All right, this will be the last video lecture of Chapter 18. I'm sure you're thrilled about that. So we've been doing nucleophilic aromatic substitution. Sorry, we haven't. We've been doing electrophilic aromatic substitution. In this video, we're going to look at nucleophilic aromatic substitution. You guys will remember nucleophilic substitution from chapter, whatever, Orgo 1, SN2, SN1. Here, so in electrophilic aromatic substitution, you substitute for an H+. Here, a nucleophile is going to substitute for a leaving group. The leaving group can be any halogen. It can even be fluorine in this case. It could be a tosylate, it could be whatever. All right, fluorine can be a leaving group in this one because the slow step is actually the addition of the nucleophile. This is 2 steps, and I'm going to go through the mechanism, and then I will show like an actual example. So the nucleophile is going to add into the ring. So the nucleophile adds into the ring, pushes the electrons toward an electron withdrawing group. So, for this to happen, you have to have at least one electron withdrawing group, and it has to be ortho, I guess I should spell this out, ortho or para to the leaving group. Okay? So if you don't have this condition met, you can't do nucleophilic aromatic substitution. So if you had a leaving group on there, say you had chlorobenzene, right? H is all the way around, this reaction can't happen. You have to have the electron withdrawing group, and I'll show an example of that. So it's addition, and we're going to see a lot of these in the last bit of Orgo 2, an additional elimination mechanism. Right, so now you have this negative charge, just come back down, kick out the leaving group, and that gets us back to an aromatic molecule where the nucleophile has substituted in. All right, so that's the general mechanism. Now let me show you an example. All right, so hit pause, try to come up with a product of this reaction. Now that you're back. So again, potassium is going to be positive, sulfur is going to be minus. We've got 2 potential leaving groups here. We've got a fluorine and a chlorine. And you guys should, from like SN2 and SN1, the carbon fluoride bond's too strong to break. But in aromatic substitution, fluoride is actually a better leaving group for reasons I'm not going to go into. The slow step is this addition step. And so once that happens, now you can break. Regenerating an aromatic ring provides the energy to kick fluoride out. All right? So the nucleophile is going to attack para or ortho to the electron withdrawing group. So chlorine's meta, so the chlorine can't leave here. So this reaction is going to give you that. And ultimately, we're going to get that plus Kf. Right? The initial adduct you get there all right, so this initial adduct that we get gives us this. And now you can see why that nitro is so important. It stabilizes that negative charge and lets you delocalize the charge out onto an oxygen. All right, so again, if you have an electron withdrawing group, ortho or para to a leaving group, the leaving groups that you know plus fluoride, then nucleophiles, and again, any nucleophile, right? All the nucleophiles you know from SN2 chemistry, SN1, well, not SN1, it's got to be a strong nucleophile. So so it's got to be something with a negative charge or some other kind of really good nucleophile. Cyanide, methoxide, hydroxide, amines, that sort of thing. So if you have a good nucleophile, you have an electron withdrawing group, ortho or pair to a leaving group, you can get a nucleophilic aromatic substitution. Never a direct attack. It's always two steps. Addition, and I didn't write this in, elimination.